Oklahoma County, 1898. While every settler raced to throw up the quickest, cheapest barn before winter, William Harrison Odor was still cutting timber in late spring. His neighbors called it wasteful. They called him a fool. He built a perfect circle, 60 feet across, 43 feet high, using green bur oak soaked in river water and bent into curved rafters. He positioned everything around a central ring, not corner posts like everyone else. He spent 6 months on a barn others finished in 3 weeks. Then the prairie storms came, supercells with rotation in the clouds, debris flying sideways, wind that found every corner and seam. Square barns failed, roofs peeled away, gable ends collapsed, corner bracing gave up. But that round barn? The wind couldn't find a flat face to grab. It rode the curve, pressure spread around the shell, and the structure flexed without breaking apart. What did Odor understand about wind, pressure, and structural engineering that everyone else missed? And how did his excessive preparation become the difference between a standing barn and scattered lumber across the prairie? If you value stories of practical wisdom that stood the test of time, make sure to subscribe. We've got more documented accounts worth remembering. Daybreak crept across the low rise above the Deep Fork River, revealing what the night's fury had left behind. The prairie stretched out like a battlefield after the cannons had fallen silent, torn boards scattered like playing cards, twisted sheets of tin wrapped around fence posts, barn doors hanging by single hinges or missing entirely. Here and there, the skeletal frames of what had been buildings stood naked against the morning sky, their contents blown clean away. But rising from this devastation, perhaps 300 yards from the worst of the wreckage, stood something that defied the storm's appetite for destruction. A red barn, perfectly round, its curved walls scuffed but unbroken, like the wind had simply flowed around it and moved on to easier prey. William Harrison Odor walked the perimeter of his creation in the pale light, his boots crunching over debris that belonged to other men's work. At 53, he had the steady gait of someone who had spent decades making practical decisions on hard ground. His neighbors would be waking soon to survey their losses, and he knew what they would find. The conventional wisdom that had built their square barns, 4 corners, straight posts, gable roofs thrown up in a matter of weeks, had met its match in the prairie wind. What they called his folly stood untouched, its curved walls and bent wood rafters having done exactly what he had calculated they would do when he first sketched circles in the dirt 6 years earlier. The mockery had started the moment he announced his intentions in the spring of 1898. Oklahoma County was still rough country then, filled with settlers who had claimed their hundreding, and 60 acres and needed to build everything from scratch before the next winter. Time was the enemy, and every day spent on elaborate construction was a day not spent breaking sod or planting crops. When Odor began talking about a round barn, his neighbors treated it like a joke that would cure itself once reality set in. A round barn? What for? So the devil couldn't corner him. The question became a standard greeting whenever he rode into town for supplies. Men who had built dozens of barns between them couldn't see the point of abandoning a system that worked well enough to keep hay dry and cattle sheltered. But Odor had been thinking about corners since his first winter in the territory. He had watched how the wind behaved around buildings, how it found flat surfaces and pushed against them until something gave way. He had seen roofs lifted clean off their frames when gusts hit the broad face of a gable end. He had watched corner joints work loose under the constant flexing that came with prairie weather. The standard approach treated wind like something to resist head-on, but Odor believed the smarter strategy was to give it nothing solid to grab. His plan required patience that his neighbors couldn't understand. While they framed their barns with milled lumber cut to standard lengths, Odor spent weeks selecting bur oak trees from his own land. The wood had to be cut green when the sap was still running and the fibers were flexible. He felled the trees in early summer and had them cut into the long, straight timbers he would need for his curved rafters. Then came the part that convinced everyone he had lost his mind. He soaked the green lumber in the Deep Fork River until the wood became pliable enough to bend without splitting. The process was labor-intensive in ways that frontier building rarely allowed. Odor constructed forms, essentially large molds, that would hold the wet timber in the precise curves he needed. Each rafter had to be bent gradually, secured in the form, and allowed to dry until it held its shape permanently. The work stretched through the summer months while his neighbors completed entire barns from foundation to roof. They would ride by his building site and shake their heads at the sight of him wrestling with bent wood and complicated joinery when straight boards and right angles would have finished the job in a fraction of the time. His brother-in-law, J. Hennon Keeley, proved to be the only man willing to commit to the experiment. Keeley understood timber work and could see the logic in what Odor was attempting, even if he couldn't predict whether it would work. Together, they developed the techniques that would make the round barn possible. They learned to judge when soaked wood had reached the perfect balance between flexibility and strength. They figured out how to join curved pieces without creating weak points where the wood wanted to split. They worked out the spacing and angles that would distribute the roof's weight evenly around the circular foundation. The foundation itself became another source of neighborhood skepticism. Instead of the standard wooden sills that most barn builders used, Odor insisted on laying up walls of local red Permian rock. The stonework took additional weeks and required skills that few frontier farmers possessed, but Odor believed that a round structure needed a foundation that could resist the sideways forces that conventional buildings rarely encountered. The rock walls rose 3 feet above ground level, creating a base that was both heavy enough to anchor the structure and solid enough to transfer loads cleanly from the curved frame to the earth below. By late autumn, when most barns were finished and filled with the season's harvest, Odor was still raising his frame. The sight of curved rafters converging on a central ring was unlike anything the county had seen. The structure was 60 feet in diameter and 43 feet high, dimensions that made it one of the largest barns in the territory. The size alone should have impressed his neighbors, but the round shape made it seem more like an oddity than an accomplishment. They couldn't understand why anyone would choose such a complicated solution when simple rectangles had served farmers for generations. The completed barn drew visitors from miles around, most of them coming to see the curiosity rather than to admire the craftsmanship. The second floor, designed for hay storage and community gatherings, could hold more people than any building in the county. The first floor provided shelter for livestock and equipment, with a circular layout that eliminated the dead corners where conventional barns collected dust and debris. But novelty wasn't the same as acceptance, and most observers left convinced that Odor had built an expensive monument to his own stubbornness. The barn stood through its first winter without incident, but that proved nothing to the skeptics. Mild weather was no test of structural integrity, and plenty of questionable buildings survived their first year. What Odor needed was validation that only severe weather could provide, the kind of storm that would reveal whether his theories about wind and corners were correct, or whether he had simply created an elaborate target for the next serious blow. In Oklahoma, that test was not a matter of if, but when. The mockery followed a predictable pattern that spring and summer of 1898. Every trip to town for supplies brought the same questions, delivered with the kind of patient amusement that men reserved for harmless eccentrics. At the general store, while Odor selected nails and hardware, someone would inevitably ask about his progress on the Fool's Circle. The name stuck with the casual cruelty of small communities, repeated until it became as natural as commenting on the weather. Children picked it up from their fathers and would point at the construction site from passing wagons, whispering about the man who couldn't build a proper barn. The social pressure was real and constant. In a territory where survival depended on proven methods and mutual assistance, deviation from accepted practice carried consequences beyond mere ridicule. When neighbors needed help with barn raisings, they called on men whose judgment they trusted. When winter storms damaged buildings, they shared materials and labor with those who built sensibly. Odor's insistence on pursuing an untested design placed him outside this network of reciprocal support, marking him as someone whose priorities couldn't be trusted when practical decisions mattered. Samuel Morrison, whose square barn sat on the next rise over, became the unofficial spokesman for conventional wisdom. Morrison had built barns in Kansas before the land run and possessed the kind of authority that came from successful repetition. He could frame a standard barn in his sleep, corner posts plumb and square, diagonal, bracing cut to precise angles, gable ends framed with triangular trusses that distributed roof loads efficiently to the walls below. His method was fast, economical, and backed by generations of frontier experience. When visitors came to gawk at Odor's construction site, Morrison would explain why circles made no sense for agricultural buildings. "You can't frame a circle with straight boards," Morrison would say, gesturing toward the complicated curves taking shape across the valley. "Every joint becomes a problem. Every angle has to be custom cut. You're creating 10 times the work for no practical gain." He would point to his own barn, completed in 3 weeks the previous autumn, and note that it held hay just as well as any elaborate structure ever could. "A barn is a tool," he would conclude. "The best tool is the one that gets the job done without fuss." The criticism was technically accurate, but missed the point that Odor was trying to make. He wasn't building a circle to be different. He was building a circle because he believed it would perform better under the specific conditions that prairie structures faced. Every conversation about his project forced him to articulate theories that sounded abstract when separated from their practical application. Wind behavior, load distribution, structural continuity. These concepts meant nothing to farmers who needed buildings that worked, not buildings that proved points about engineering principles. But Keeley understood what his brother-in-law was attempting, and his willingness to commit labor to the project gave Odor the credibility he needed to continue. Keeley had spent years working with timber and recognized quality craftsmanship even when it served an unfamiliar purpose. The curved rafters that Odor was creating through his soaking and bending process were superior pieces of wood, stronger and more flexible than anything that could be achieved with conventional cutting and joining techniques. The joinery required to connect these pieces was complex, but it was also precise in ways that standard construction rarely achieved. The actual construction process became a public spectacle as word spread beyond the immediate neighborhood. Farmers would ride miles out of their way to witness the daily progress on the round barn, bringing their families for Sunday visits that combined entertainment with education. Children climbed on the growing foundation walls while their parents debated the merits of Odor's approach. Most visitors left convinced that they were watching an expensive mistake unfold, but a few recognized the sophistication of what was being attempted. The foundation work alone demonstrated levels of skill that frontier building rarely required. Laying up walls of local red Permian rock demanded knowledge of stonework that most farmers didn't possess. Each stone had to be selected for its shape and structural properties, then fitted into place with minimal mortar. The resulting walls were 3 feet high and thick enough to provide a stable base for the unusual loads that a circular structure would generate. The stonework was slow, meticulous, and completely unlike the simple wooden sills that supported conventional barns. As summer progressed and the frame began to rise, the technical challenges became visible to anyone who understood building. The curved rafters had to be cut to precise lengths and angles, with each piece fitting into the overall structure at predetermined points. The central ring that would support the peak of the roof required joinery techniques that most carpenters had never attempted. Every connection had to be engineered to handle forces that acted differently than they did in rectangular buildings. The timber preparation process drew particular scorn from practical men who valued efficiency above experimentation. Odor's method of cutting bur oak green, soaking it in the river, and bending it in forms struck them as wasteful of both time and materials. Conventional framing used seasoned lumber cut to standard dimensions, with joints that could be cut quickly using established patterns. Odor's approach required individual attention to each piece, with custom measurements and angles that couldn't be duplicated from barn to barn. Morrison would bring visitors to watch the bending process, using it as an object lesson in why traditional methods remained superior. "Look at that waste of effort," he would say, pointing to timber that had been soaking for weeks. "By the time he gets one piece shaped, I could frame an entire wall section. And what happens when one of those custom pieces breaks? You can't ride to town and buy a replacement. You have to start the whole process over again." The criticism was logically sound, but ignored the performance characteristics that Odor was trying to achieve. His bent rafters would be stronger than straight-cut lumber because the grain followed the curve instead of being interrupted by cuts and joints. The custom joinery would create connections that distributed loads more evenly than standard corner bracing. The circular shape would handle wind loads differently than rectangular structures, spreading forces around the perimeter instead of concentrating them at vulnerable points. As autumn approached and conventional barns stood completed and ready for the harvest season, Odor's project remained unfinished. The sight of exposed framing and incomplete walls reinforced every criticism that had been leveled against the design. Practical farmers needed their buildings ready before winter, and delays carried real consequences in terms of crop storage and livestock shelter. The round barn had become a symbol of impractical theorizing that ignored the realities of agricultural life. But Keeley continued working alongside his brother-in-law, and together they maintained the pace that the project required. The complexity of the construction meant that rushing would compromise the structural integrity they were trying to achieve. Every joint had to be fitted properly, every connection had to be secure, and every piece had to contribute to the overall strength of the finished building. The work was methodical, precise, and completely unlike the speed-driven approach that frontier conditions normally demanded. By late November, when the first serious cold arrived, the round barn finally stood complete. The finished structure was 60 feet in diameter and 43 feet high, with 2 full stories and a roof that curved seamlessly from the central peak to the circular wall below. The building was undeniably impressive in scale and craftsmanship, but impression wasn't the same as vindication. What Odor needed was proof that his theories about wind and structural behavior were correct, and that proof could only come from the kind of severe weather that tested every building to its limits. The fundamental difference between Odor's barn and every other structure in the county lay in how each design responded to the basic physics of wind pressure. When air moving at high velocity encountered a flat surface, it behaved like water hitting a dam. The moving mass had to go somewhere, and that somewhere was usually around the edges and over the top, creating turbulence and pressure differentials that could tear buildings apart. Morrison's square barn, like every conventional structure on the prairie, presented 4 flat walls to approaching storms, each one acting as a solid barrier that forced the wind to pile up, accelerate around corners, and create the kind of chaotic airflow that found weak points in construction and exploited them. Odor had observed this phenomenon during his first years in the territory, watching how wind behaved around different shapes and surfaces. He noticed that round objects, water tanks, grain silos, even large trees with full canopies, seemed to shed wind more efficiently than angular structures. The air flowing around a curved surface remained more organized, following the contour instead of breaking into the violent eddies that formed downwind of flat walls. This observation led him to conclude that a circular barn would handle prairie storms more effectively than rectangular designs, not by resisting the wind, but by redirecting it. The engineering principles involved were straightforward once the basic concept was understood. Wind pressure increased dramatically with velocity. A doubling of wind speed created 4 times the force against any surface in the airstream. At 60 miles per hour, the pressure against a flat wall reached roughly 9 pounds per square foot. At 100 miles per hour, that pressure jumped to 25 pounds per square foot. For a barn wall 40 feet high and 60 feet wide, those numbers translated to forces that could exceed 500,000 pounds during severe storms. Conventional barns tried to resist these forces through bracing and structural mass, but Odor believed that avoiding the forces entirely was a more effective strategy. The circular design accomplished this avoidance by eliminating the flat surfaces that created pressure buildup in the first place. Instead of hitting a wall and piling up, wind approaching the round barn encountered a curved surface that gradually deflected the airflow to either side. The pressure against any given point on the circular wall was significantly less than the pressure against a flat surface. And more importantly, the forces were distributed around the entire perimeter instead of being concentrated at corners where structural failures typically began. Morrison's barn demonstrated the conventional approach to wind resistance through its standard post and beam construction. The building relied on 4 corner posts to carry the primary loads, with diagonal bracing designed to prevent the rectangular frame from distorting under lateral pressure. The system worked well under moderate conditions, but it created specific failure points where extreme forces could overwhelm individual components. If one corner post shifted or one brace failed, the entire structure could lose its integrity in a cascade of progressive collapse. The gable ends presented particularly vulnerable targets during severe storms. These triangular wall sections, necessary for conventional roof designs, acted like sails when hit by high winds. The broad, flat surfaces caught every bit of airflow and transmitted the resulting forces directly to the frame structure below. Worse, the peaked shape created uplift forces that tried to lift the roof off the building entirely. Many prairie barns lost their roofs long before their walls failed, leaving the contents exposed to wind and rain. Odor's circular design eliminated these vulnerability points through its continuous ring structure. Instead of concentrating loads at four corner posts, the round barn distributed weight and wind forces around its entire perimeter. The curved rafters that formed the roof were joined at a central ring, creating a system where each timber helped support its neighbors. If one section of the structure came under severe stress, the loads were shared by adjacent members instead of accumulating at a single failure point. The bent wood rafters contributed to this load-sharing capability in ways that straight lumber could not match. Each rafter had been shaped from a single piece of bur oak, with the grain following the curve from the central ring to the circular wall. This meant that the structural member was strongest along its entire length, without the weak points that occurred wherever straight pieces were joined together. The soaking and bending process had also made the wood more flexible, allowing it to deflect under extreme loads without breaking. The foundation design reflected the same principles of distributed loading that governed the frame structure above. Instead of relying on isolated footings under corner posts, the red Permian rock walls formed a continuous ring that transferred all structural loads to the ground evenly. The circular foundation also provided superior resistance to the sideways forces that could shift conventional buildings off their footings during severe storms. The shape itself was inherently stable, like an arch laid flat against the ground. The roof system represented perhaps the most sophisticated aspect of Odor's design. Instead of the simple gable configuration used on rectangular barns, the round barn employed a conical roof that peaked at the center and sloped evenly in all directions. This shape eliminated the flat surfaces that created uplift forces while providing the curved profile that encouraged smooth airflow over the building. The central ring that supported the peak was engineered to handle loads from every direction simultaneously, distributing the forces so that no single connection carried more weight than it was designed to bear. The structural continuity of the circular design meant that the building functioned as a unified system rather than an assembly of separate components. The foundation, walls, and roof were all integrated parts of a single load path that transferred forces efficiently from the point of application to the ground. This integration gave the round barn a resilience that conventional structures could not match, because failure of any individual element did not compromise the integrity of the whole. Keeley understood these principles through his experience with timber construction, even though he lacked the theoretical framework to explain them in engineering terms. He could see that the curved rafters were stronger than straight lumber, and that the circular frame was more stable than rectangular construction. His willingness to commit labor to the project reflected his confidence in the craftsmanship involved, regardless of whether the underlying theories proved correct. The finished barn embodied these design principles in physical form. The 60-foot diameter created a structure large enough to demonstrate the advantages of circular construction while remaining manageable from a building standpoint. The 43-foot height provided adequate interior space, while keeping the proportions reasonable for the foundation and frame to support. The two-story design allowed the building to serve multiple functions while testing the structural system under realistic loads. What remained to be proven was whether these theoretical advantages would translate into superior performance under actual storm conditions. The prairie had a reputation for delivering the kind of severe weather that tested every assumption about wind and structural engineering. When that test came, the round barn would either validate Odor's theories or demonstrate that conventional wisdom existed for good reasons. The building stood ready for either outcome, its curved walls and bent wood frame representing years of careful planning and meticulous construction that would soon face the ultimate judgment of Oklahoma weather. The storm season of 1902 arrived with the kind of meteorological violence that reminded settlers why the prairie had remained largely unsettled for so long. The weather patterns that spring developed with ominous regularity, massive supercells forming over the Texas Panhandle and tracking northeast across Oklahoma Territory, each one carrying the potential for destructive winds, hail, and the rotating columns of air that could level entire homesteads in minutes. By early May, the atmospheric conditions had aligned in ways that veteran plainsmen recognized as particularly dangerous, with strong upper-level winds, abundant moisture, and the temperature contrasts that fed severe thunderstorms. The storm that would test every theory about wind and construction began forming on the afternoon of May 15th, building slowly over the Red River Valley before gaining strength as it moved across the rolling hills of central Oklahoma. Weather observers in Oklahoma City, 30 miles to the southwest, recorded barometric pressure drops that indicated a system of unusual intensity. The advancing storm front stretched across the entire visible horizon, its leading edge marked by a wall of roiling black clouds that seemed to swallow the landscape as they approached. Odor spent the late afternoon securing loose equipment around his property while keeping one eye on the approaching weather. The round barn stood ready for whatever the storm might bring, its curved walls and bent wood frame representing 4 years of theory and craftsmanship that would soon face the ultimate test. The building had weathered numerous smaller storms since its completion, but nothing approaching the scale of what was bearing down on the county that evening. The wind was already gusting to 30 miles per hour, and the real blow hadn't even arrived yet. Morrison and his neighbors were making similar preparations at their own homesteads, bringing livestock under shelter and battening down anything that might become projectiles in high winds. The conventional barns that dotted the landscape had survived previous storms through a combination of solid construction and good fortune, but the approaching system carried the kind of power that could overwhelm any structure not specifically designed to handle extreme conditions. The barometric pressure continued dropping as the storm front approached, creating the atmospheric instability that fed the most violent weather. The first serious winds arrived just after sunset, gusting to 60 miles per hour and driving horizontal sheets of rain across the prairie. The temperature dropped 15 degrees in as many minutes, creating the thermal contrast that marked truly dangerous storms. Lightning began striking with increasing frequency, illuminating the landscape in stark flashes that revealed the storm's enormous scale. The thunder that followed was continuous rather than intermittent, indicating that multiple cells were active simultaneously across a broad area. Morrison's barn faced its first real test as the wind speed climbed past 70 miles per hour. The rectangular structure presented its full 40-foot-high gable end to the approaching storm, creating exactly the kind of flat surface that caught wind like a sail. The building began to flex under the pressure, its frame transmitting the loads down through the corner posts to the foundation below. The diagonal bracing that provided lateral stability was working hard, but the forces were building beyond anything the structure had experienced since construction. At 80 miles per hour, the pressure against Morrison's gable end was approaching 13 pounds per square foot across the entire surface, nearly 20,000 pounds of force pushing against the triangular wall section. The building was designed to handle these loads, but the margin for error was shrinking as the wind continued to intensify. The roof began to lift slightly with each major gust, the entire structure acting like a partially open box that was trying to take flight. Odor's round barn was experiencing the same wind speeds, but responding completely differently to the forces involved. Instead of catching the wind against flat surfaces, the curved walls were deflecting the airflow smoothly around the building's perimeter. The pressure against any given point on the circular wall remained well below what Morrison's flat surfaces were experiencing, and more importantly, the forces were being distributed around the entire ring structure instead of concentrating at vulnerable corner connections. The critical moment arrived when the wind speed exceeded 90 miles per hour and began gusting past 100. At these velocities, the pressure against flat surfaces jumped to more than 25 pounds per square foot, creating forces that could overwhelm structures not specifically designed for extreme conditions. Morrison's barn reached its structural limits as the gable end began to deflect visibly under the enormous pressure. The corner post connections were working loose under the repeated stress cycles, and the roof was lifting several inches with each major gust. The failure began at the northwest corner, where the constant flexing had loosened the connection between the corner post and the main beam that supported the roof structure. Once this joint began to separate, it created a cascade effect that spread throughout the frame. The diagonal bracing that was supposed to prevent this kind of distortion was overwhelmed by forces beyond its design capacity. Within minutes, the entire gable end was shifting out of alignment, taking the roof structure with it. The collapse happened with the sudden violence that characterized structural failures under extreme loads. The northwest corner gave way completely, allowing the roof to twist off its supports and partially collapse into the interior of the building. The remaining walls were left without adequate bracing, and they began to fold inward under the continuing wind pressure. What had been a solid barn just minutes earlier was reduced to a pile of broken lumber and twisted metal roofing that would take weeks to clear away. Other conventional barns throughout the county experienced similar failures as the storm reached peak intensity. The rectangular designs that worked well under normal conditions proved vulnerable to the extreme forces that accompanied winds over 100 miles per hour. The flat surfaces that were necessary for conventional construction became liabilities when subjected to the kind of pressure that accompanied severe prairie storms. Buildings that had stood for decades were reduced to debris in a matter of minutes. Odor's round barn rode out the same conditions with dramatically different results. The curved walls continued to shed wind efficiently, even as velocities peaked above 100 miles per hour. The bent wood rafters flexed under the extreme loads, but maintained their structural integrity because the forces were distributed through the ring system rather than concentrated at corner connections. The building moved and creaked under the assault, but the fundamental structure remained sound. The most telling evidence of the design's superiority came during the storm's final phase, when shifting wind direction subjected all structures to forces from multiple angles. Rectangular buildings were vulnerable to this kind of attack, because their strength was optimized for loads coming from specific directions. The round barn, by contrast, was equally strong regardless of wind direction because its circular symmetry meant that every point on the perimeter was identical in terms of structural capacity. When dawn broke over the devastated landscape, the contrast was unmistakable. Debris from failed structures littered the prairie for miles, marking the path of destruction that the storm had carved across the territory. Morrison's barn was gone, reduced to scattered lumber that would never again provide shelter for crops or livestock. Other conventional buildings throughout the area had suffered similar fates, their rectangular designs proving inadequate for the forces that prairie storms could generate. But the round barn stood essentially undamaged, its red walls and curved roof intact, despite having endured the same conditions that had destroyed buildings throughout the county. The structure showed signs of stress, some minor settling in the foundation, a few loose boards in the siding, but nothing that couldn't be repaired with routine maintenance. More importantly, the building had remained functional throughout the storm, providing secure shelter for the livestock and equipment it was designed to protect. The physical evidence was overwhelming and undeniable. Odor's theories about wind pressure and structural design had been validated in the most dramatic way possible, while conventional wisdom lay scattered across the prairie in pieces too small to salvage. The morning after the storm brought visitors from across the county, drawn by reports of the round barn's survival when so many conventional structures had failed. Men who had mocked Odor's design just days earlier now walked the perimeter of the building with quiet reverence, examining the curved walls and bent wood frame that had withstood forces powerful enough to level their own barns. The mockery that had followed the project for 4 years evaporated in the face of undeniable physical evidence, replaced by a grudging respect for methods they had dismissed as foolish. Morrison was among the first to arrive, picking his way through the debris field that had been his barn, while casting frequent glances toward the intact circle on the neighboring rise. The man who had served as the unofficial spokesman for conventional wisdom found himself without answers when confronted with the stark contrast between his scattered lumber and Odor's standing structure. The theoretical arguments that had seemed so compelling during construction now appeared hollow when measured against actual performance under extreme conditions. The questions began tentatively, posed by men who were reluctant to admit that their certainty had been misplaced. How had Odor bent those rafters without breaking them? What kept the circular frame from distorting under the tremendous loads? How had he calculated the proper dimensions for a structure unlike anything they had built before? The inquiries reflected genuine curiosity rather than polite interest, driven by the immediate practical need to rebuild and the recognition that conventional methods had proven inadequate. Odor answered with the patience of someone whose theories had been vindicated, but who took no pleasure in his neighbor's losses. He explained the timber-soaking process that had made the curved rafters possible, demonstrating how green bur oak could be bent into permanent curves through careful application of moisture and controlled drying. He described the load-sharing principles that distributed forces around the circular frame instead of concentrating them at corner connections. He walked visitors through the foundation design that transferred structural loads evenly to the ground rather than relying on isolated footings under corner posts. The technical explanations were received with the attention that practical men reserved for information they needed to use. These were not abstract theories anymore, but proven methods that had demonstrated their value under the most severe conditions the prairie could deliver. Several farmers began making sketches and taking notes, recognizing that the round barn represented knowledge they could not afford to ignore when planning their own reconstruction efforts. Keeley found himself in demand as visitors sought details about the actual construction process. His hands-on experience with the bending techniques and specialized joinery made him the expert on translating Odor's theories into practical building methods. He explained how to judge when soaked timber had reached the proper flexibility, how to construct the forms that held curved pieces while they dried, and how to join bent wood without creating weak points where splits might develop. The information was valuable because it represented the difference between successful implementation and expensive failure. Word of the round barn's performance spread beyond the immediate neighborhood as reports of the storm's destruction reached communities throughout the territory. Agricultural journals began requesting details about the unusual design that had survived when conventional structures failed. Engineering publications expressed interest in the principles that had made circular construction superior to rectangular building under extreme wind conditions. The barn that had been dismissed as an expensive folly was becoming recognized as an important innovation in prairie architecture. The validation brought practical benefits that extended beyond personal satisfaction. Farmers who were rebuilding after storm damage began consulting with Odor about incorporating circular elements into their own construction projects. Some requested complete round barns built using his methods, while others asked about hybrid designs that combined curved elements with more conventional rectangular layouts. The demand for his expertise transformed Odor from an eccentric experimenter into a recognized authority on wind-resistant construction. The round barn itself became a community gathering place in ways that its original design had anticipated, but that took on new significance after its dramatic vindication. The second-floor space that had been intended for meetings and social events now served as a symbol of practical wisdom, triumph over conventional thinking. Barn dances held in the circular space drew participants from throughout the county, with the building's survival story becoming part of the entertainment as visitors marveled at the curved rafters and ring construction that had proven superior to traditional methods. Odor's reputation spread beyond Oklahoma territory as word of his innovation reached builders and engineers in other regions where severe weather posed similar challenges. Letters arrived from Kansas, Nebraska, and Texas requesting detailed plans and construction specifications for round barns. Agricultural colleges expressed interest in studying the design principles that had produced such superior performance under extreme conditions. The local experiment that had begun as one man's theory about wind in corners was evolving into a recognized advancement in structural engineering. The success brought opportunities that extended well beyond individual building projects. Timber companies began advertising specially prepared curved lumber for round barn construction, using Odor's techniques for soaking and bending bur oak into the precise shapes that circular frames required. Hardware manufacturers developed specialized connectors designed for joining curved members at the angles that ring construction demanded. An entire industry was emerging around methods that had originated from one farmer's observations about how wind behaved around different shapes. Frank and Katie Verana, who would later acquire ownership of the barn, represented the next generation of practical users who valued the structure for its proven capabilities rather than its novelty. Their approach to the building was utilitarian, using it for hay storage, livestock shelter, and general farm work, but their continued reliance on the round design validated its long-term practicality. The barn that had begun as an expensive experiment had evolved into a trusted tool that served the same functions as conventional structures while providing superior performance under severe conditions. The legacy extended beyond individual buildings to influence broader thinking about structural design and wind resistance. Engineering textbooks began, including sections on circular construction and load distribution principles that Odor had demonstrated through practical application. Architecture schools taught the round barn as an example of form following function, where unusual appearance served specific performance requirements rather than mere aesthetic preference. The building that had been mocked for its unconventional appearance became recognized as an elegant solution to a fundamental engineering problem. Luke Robison's later restoration work, following the roof collapse of 1988, demonstrated that the principles underlying the round barn remained valid more than 90 years after its original construction. The volunteer effort required to rebuild the complex curved roof system showed that the methods Odor had developed were still challenging to execute, but that the performance advantages justified the additional effort required. The restored barn that reopened to the public in 1992 served as both a historic monument and a continuing demonstration of superior structural engineering. The round barn's vindication established a principle that extended beyond individual building projects to broader questions about innovation and conventional wisdom. The structure proved that careful observation of natural phenomena could lead to solutions superior to accepted practice, but only when combined with the willingness to invest time and effort in unproven methods. The barn that had survived when others failed became a permanent reminder that on the prairie, you don't beat the wind by standing against it. You beat it by building so the wind can't get a hold of you.